Hi everybody, and welcome to part 9 of the Bravo project. So in this video, we will continue our discussion of our memory module. If you have watched part 8, we actually built this module, including the memory address register, the RAM, the flash memory, and all the control circuits. But also, we tested the memory address register and our RAM. Now, in this video, we will be focusing on our flash memory. And essentially, we're going to talk about why flash memory instead of an EEPROM, and also a little bit about internals of this specific chip and how it works. And then we're going to basically go ahead and test it. Now, with that, let's have a look at a couple of slides just to review what we have so far. And then we're going to have a look at the circuit, and then eventually we're going to go ahead and test our flash memory. All right, with that, let's get started. All right, so let's have a look at our flash memory circuit and see how it is connected to our memory module. Now, before going through the circuit, I would like to actually use a couple of slides here just to better understand our flash memory, and then we're going to come back to the circuit. Now, if you remember from the previous video, we talked about the memory address register, which is a 16-bit register that outputs, 16 bits on the output side. Now, out of that 16 bits, we were using 15 bits for addressing, and we were using the most significant bit as a chip selector. So in case of RAM that we talked about in the previous video, the address lines that are outputting from our memory address register were all directly connected to address line of our RAM. You know, our RAM is a 32K RAM. Therefore, the 15 bits output from our memory address register were enough to address the whole memory, right? Because we have 15 bits, and 2 to the power of 15 will be 32K of addressing. So that was easy enough, right? So address lines A0 will connect it to A0 on the RAM, A1 to A1, A2 to A2, and so on. We are also using the most significant bit output from our memory address register as a chip selector, right? And I talked about that the output of this most significant bit actually is going through a little circuit here that enables us to activate or enable one of these chips at each point of time. So if this bit is actually going high, then we have our RAM basically chip enabled and flash memory disabled. And when this bit actually goes low, then we had our flash memory chip enabled and our RAM be disabled. And of course, both of these chips have some, outputs that are connected to our bus. Now, in case of RAM, it was quite easy because, again, we had 32K of addressing available to us, and the RAM is only 32K. However, in case of flash memory, it's going to be a challenge because our flash memory is actually a 512K flash memory. So obviously, just using these 32K addressing that we have available here, we would not be able to address the whole flash memory. And if you think about it, if we actually have a 512K of memory inside our flash, then we probably have more address lines to address those, right? And this is actually true. Our flash memory chip has 19 address lines, starting from A0 all the way up to A18. However, the first 15 address lines, meaning that from A0 to A14, is directly connected to our memory address register, just like our RAM. So A0 to A0, A1 to A1, and so on. However, we are left with 4 more bits, which are actually the most significant bits on this chip that are not connected to our memory address register. Therefore, we could not address them using our memory address register. So we have to actually come up with a different mechanism here in order to address the remaining 4 most significant bits in these flash. And that's why we have a circuit here, which we call it a bank selector. The output of this circuit is connected actually to those 4 most significant bits in our flash. And using that little circuit, we are controlling these 4 lines. And obviously the remaining lines, the remaining address lines, are connected to our MAR. So this 4-bit bank selector is essentially just another register that has some inputs from the bus side. And the output of this simple 4-bit register is actually connected to address lines of 15 to 18. Now, probably we need to go to the next slide to have a better understanding of how this thing works. Now, as you can see here, this bank selector circuit here will be outputting 4 bits, right? So we could actually set any value between 0 and 15 on the bus, and then read it into this register, and obviously output those to those address lines from A15 to A18. Now, look at these slide. You notice that, let's say that we actually have all the address lines from A15 to A18 set to 0 as the first step, right? And this is actually the default. When we are resetting the computer, all of those address lines are set to 0. Now, in this case, if we actually just use our memory address register to address the flash, you know that our memory address register has 15 bits for addressing. Therefore, it could address from 0 all the way to 32,767, right? So all the 32K, the first, let's say 32K on the chip, could be actually directly addressed through our memory address register. From a flash memory's perspective, it's again going to be the same because, again, these bits, the most significant bits, are all set to 0. Therefore, flash memory also sees that as address 0 all the way to address 32,767. Now imagine that now we want to actually output 1 from our bank selector. So if you output 1, then that means that the A15 line here will be set to 1, right? This is a 4-bit number that we are outputting from register. Therefore, the A15 address line will be set to 1. Now, if you think about it, since we are actually addressing to a higher memory space using this line, we have access to another 32K space here, which from the memory address register's perspective, it still counts as a memory space from 0 all the way up to 32,767. However, from a flash memory's perspective, since this bit is high, then it's actually a different memory space from 32,768 all the way up to 65,535, right? So essentially, we are actually pointing to a different section of our memory, flash memory, just by changing this, bit on the A15 line. And following the same thing, if you think about it, this 4-bit bank selector could actually output 16 different values from 0 all the way to 15. Therefore, we could actually have a total of 16 banks here, and each bank is actually a different memory space with a capacity of 32K, right? So hopefully it is clear and it's understandable. But in general, if you look at it, you could imagine that at each point of time, we are actually pointing to one of these banks, meaning that we could not obviously read or write to, let's say, 2 or 3 of those banks at the same time, because obviously our bank register or bank selector will be pointing to a specific bank, and then inside that bank we have access to 32K of memory. And that's how basically we cover all the 512K memory space inside our flash. Essentially, we just have a circuit that controls the 4 most significant bits, and by changing the value on those bits, we would be able to actually point to a different memory section in our flash. Now, selecting those flash memory spaces are quite easy. We just set a value from 0 to 15 on our bus. We read that value into our bank register. We output that into our address lines. And then once the address lines are set, the combination of this bank selector along with the output of the memory address register will give us access to different spaces in our memory, or what we call it, our banks. Now, something to mention here is that, remember, these division of our flash memory here is completely logical. This is just basically what we came up with just because we only have 32K of addressing output from our MAR. This is not something that actually, designed or architectured in the factory for this chip. This is just our solution to be able to divide that big, flash memory space into different banks, right? From the flash memory's perspective, it is just a continuous, memory address from 0 all the way to, 512K. But again, here we are just need to be creative and kind of come up with these banks and logically, and I would say artificially, divide the our flash memory to different banks. All right. So with that, let's go back to the circuit and see what basically we have there. So after going through those slides, I guess the circuit will be quite easy to look at. So as I said, we have a total of 19 address lines from A0 all the way to A18. And the first 15 of those are connected to our memory address register, just like our RAM. So A0 all the way to A15, all the way to A14 are connected to the output of the memory address register. However, the address lines of 15, 16, 17, and 18, as you can see here in the circuit, is actually connected to our bank selector. And I'm going to talk about that bank selector in a minute. So these are the address lines for our flash. The output lines are connected to bus, obviously, from bus 0 all the way to bus 7. And using those bus lines, we could either read data from the bus or write something to our bus. So quite easy. So other than these address lines and the bus lines, what is left really is 3 signals. And we are already familiar with those 3 signals if you have watched the previous video. Just like our RAM, we have a RAM out signal, which actually comes to pin number 24, which is output enable in our flash memory. And it's active low signal, meaning that whenever we actually want to put the content of the memory on the bus, we just bring this line low, and that outputs the content of the memory into the bus. So that is, I believe, quite clear. The other signal is the chip enable, which again, we talked about that in previous video. It is just an active low signal connected to pin 22 to select this chip and enable this chip, which again connected to our chip selector circuit that we talked about in the previous video. So that should be quite clear now. And then the final signal is really the write enable, and we're using the same signal that we were using in case of our RAM, which basically just RAM in signal combined with the clock signal that actually comes to write enable pin, which is pin number 31 here. And by bringing this line low, we are actually writing to our flash memory from the bus, right? So I hope that those signals make sense by now after going through this. Now, let's talk about that flash bank selector circuit. So as we know by now, the address lines A15 to A18 are actually connected to output of this register. And this register is basically a 74HC173 chip, which is basically a D-type flip-flop register. And it has some inputs that are connected to a bus side and also some outputs, which are obviously connected to our address lines. And also it has some control signals. Now, the output side of the chip, the control signals for the output side are called output enable 1 and output enable 2. As you can see, both of those pins are actually tied together and tied to ground. That means that we are actually permanently outputting, the data on this chip. We are not controlling the output side of these chip using a signal. We just, permanently outputting whatever is on the chip on the output lines, and that is fine. Basically, whenever we reading a value from the bus into the chip, it will immediately show up on the output side. There is no need to control the output enable. However, on the input side, again, we have two pins, pin number 9 and 10, that you can see are tied together and actually controlled by some control signals. And this is again an active low signal, and whenever we want to read something from the bus, we just need to bring both of these lines, basically E1 and E2 low, so that we read the value from the bus and basically put it into our register. Now, other than that, we have obviously a clock pulse signal here that comes to pin 7, and obviously whenever you want to read something from the bus, we need to pulse the clock. So this is simple. And finally, we have a master reset pin here, and this master reset in this specific chip is actually an active high signal, and that's why you see that we have an inverter that actually brings the main reset lines from our computer and inverted it before going to the chip. The main reset signal in our computer is actually an active low signal. So this signal is connected to multiple chips in our computer, and whenever we bring this line low, it will basically reset all of those chips to let's say 0. However, in the case of this specific chip, this is an active high, and that's why we need an inverter just to be consistent, obviously, with the rest of the computer. When this line goes low and everybody else is resetting, this inverter basically makes this signal high, and of course this chip will be reset. So now let's talk about the control signal. So as I said, the control signal should be an active low signal coming to pin 9 and 10. However, if you look at the circuit, we are actually combining two other signals through a NAND gate in order to make that specific control signal. And those two signals are EC and HI. And by now, you should probably be familiar with both of these signals because we talked about those actually in the previous videos. For example, EC is actually one of the signals that we were using in our ALU circuit to add 1 when we were making the 2's complement. And then HI signal was the signal that we were actually using to, let's say, activate the high byte of a circuit, right? However, the beauty of this computer is that we are actually recycling a lot of signals, and we are using different signals by combining them together to come up with a unique signal. That means that we are not actually outputting a, let's say, specific dedicated signal just to control our bank. We are using the same signals that we had in the previous circuits that actually may do a different thing. As I said, the EC is actually doing a completely different thing in our ALU. The HI is doing a completely different thing in a couple of circuits. But just by combining these signals here, we could come up with a completely unique combination here and completely unique control signal to just, let's say, control our flash memory bank. So in this case, whenever you want to actually read something from the bus and put it in our register, bank register, what we could do, we could bring the EC and HI signals both high. And when we bring both of those high, obviously the output of the NAND gate will be low. And that's what we need to actually enable this register and read the data from the bus and save it into our register. Now, this combination of EC and HI here is quite unique, and meaning that in no other operation in this computer, we actually have both of those signals high at the same time, right? So if If it's actually unique here, that means that we could just use the same signal, and basically whenever we want to control the bank, we could just bring those high, and therefore control our register. All right, so hopefully everything is clear so far. Now there's another part that we need to talk about when we're dealing with our flash memories. And if the subject has not been complicated enough so far, I actually wanted to make it more complicated now. This is in regard to the write operation on this specific flash memory. And in general, basically this applies to most of the flash memories that are available out there in the market. That the write operation on these flash memories is not as straightforward as, let's say, a RAM chip. In case of RAM, when you have a data on the bus, you could just simply, let's say, bring the write enable line low, and that would cause that data from the bus to be written into our RAM chip. However, in case of the flash memory, this is not as simple as that. Essentially, these flash memory chips have a protection mechanism in order to prevent accidental writes on these chips. Basically, every time that you want to write anything to those chips, first you need to follow a specific procedure and send specific data to specific addresses in order for the chip to basically be able to write anything into it. So in order to further clarify this point, we actually need to have a look at the documentation for these chips. So let's have a look at the datasheet for this specific chip that we are working on. We are actually using two versions of this chip, which is SST39 SF010 and 39 SF040. The 010 version is a 128K model, which we will be using two of these chips in our control logic, which we will be building later in the project. However, the SF040 is a 512K model, which we just talked about it in the memory circuit. So let's have a look at some of the important aspects of these chips, just to clarify what we need to do actually for a write operation. I mean, first of all, we need to understand that we have a limited number of write cycles available with these chips. That means that you could not actually write indefinitely into those chips, and each time that you're writing to it, you're actually reducing the number of cycles available for future write operations. I guess with each write operation, essentially, I think those chips are degrading or something like that. And here in the documentation is talking about 100,000 cycles. It's a lot of cycles, but again, I'm not sure how actually those write cycles are calculated. I went through the documentation, but it's not still completely clear that how actually these write cycles are calculated. So if someone knows about that and have more information, I would appreciate it if you, write a comment about it. Now, in regard to the chip itself, there are a couple of things that we need to look at it, and probably one important thing here is that we also have a concept of sectors in these flash memories. So each of those flash memories from factory are actually divided to uniform 4 kilobyte sectors. And we're going to come back to this point in a minute. So let's have a look at the documentation. And the first thing is you get a block diagram here of the circuit, internal basically circuit of the flash memory, which talks about the chip enable, output enable, and write enable signals coming to a control logic inside the chip. And then, of course, we have the DQ0 to DQ7 outputting from I/O buffers. And you could probably read the documentation on that and get an idea how the chip works. But in general, I just would like to highlight a couple of points here, which I think are important, and these are related to the device operation. So for a read operation, it is quite simple and straightforward. Just like our RAM, we have an output enabled pin, which is an active low pin. And by bringing this pin low, we would be able to read the content of the memory and basically put it on the bus. And if you remember from the circuit, this output enable pin is actually connected to our RAM out signal. So read operation is quite easy. However, the write operation is a little bit more involved. And that means that in order to write something to the chips, which here is referred as byte program operation, first of all, you need to actually do the write operation byte by byte, meaning that at each point you're just writing 1 byte, and then you basically have to again follow the same procedure for the next byte and so on. Another important thing here is that before programming any byte, the sector that actually where the byte is going to exist must be fully erased, as you can see here in the documentation. So that means that we actually have a concept of sector and some sort of division inside these flash memory chips. And if you read more, you see that it said the program operation is actually accomplished in 3 steps. The first step is the 3-byte load sequence for software data protection, which basically refers to SDP, or the software data protection mechanism, which protects the chip from random writes. Essentially, again, as I said, you need to follow a specific procedure to write to those chips before being able to write to them. And of course, he's talking about the different steps that are involved and so on. But we're gonna look at that shortly. So if you go down the documentation, you would notice that here it talks about the SDP and what it is, and basically how it helps you to avoid unwanted writes to the chip. However, here, if you go down, there's a table called software command sequence, which I guess contains basically everything that we need to write or erase this type of flash memory. Now, first thing, as we just read from documentation, in order to actually write to the chip, first we need to erase a sector that byte will be written to. So that basically means that we have a concept of sectors here that we need to look at it and see what are these sectors. And then also I would like to mention that for each, let's say, erase operation or even programming operation or writing operation to the chip, you actually have to follow specific steps, or what we call it here, the cycles or write cycles. So that means that, for example, if you actually want to erase a sector, first you need to point to a very specific address in the memory, which in this case at stage 1 is 5555 in hex, and this H here is just indicating that this number is actually a hex number. So that means that first you need to point to this hex address in the memory, and then you have to write the specific value to that memory address. And this is going to be your step 1. Then you have to follow that step with step 2, which means that pointing to a different memory address and writing a different data in there, and so on. So you can see that just for erasing a sector, you actually have to go through 6 cycles. And in the last cycle, you actually pass the sector number. Again, I'm going to talk about sectors in a minute. But you're gonna pass in the sector number, and also you're gonna send the specific command, which basically erases the sector. Now, when the sector is erased, now you can go ahead and start writing to the chip, which again involves 3 initial cycles before even getting into the writing the actual data into the chip. And as you can see, again, in the first cycle, you're pointing to a specific memory address, and then you're writing AA, let's say in the first cycle. The second cycle has specific address and data, and finally, the last cycle that before writing the data also has its own, specific address and value. And eventually, at stage 4 or step 4, you could actually point to your intended target address, and then you're going to send your data to be written to that address, and that's going to be basically just a byte that you want to write to that address. And interestingly, for the next byte, you actually have to go through the whole procedure again. So as you can see, writing to these chips is a little bit more involved than just, writing into, let's say, a RAM chip. But don't worry about it, despite the fact that it looks a little bit complicated here. In reality, it is not that difficult. I mean, we're going to have a look at the sketch that I wrote for the write operation, and you would see that I'm actually sending those datas and setting the addresses and sending those datas back to back, and then I'm basically sending the final data that I want to write to the chip quite easily using an Arduino sketch that we're going to look at it later. So with that, let's now focus on the sectors. So what are sectors and how we should treat them? Now, in order to look at those, I need to go back to my slides and basically just show you a little bit more about what is happening inside those flash memories. So let's first focus on the 512 kilobyte flash memory version that we are actually using in our memory module. As you can see, this 512 kilobyte space on our flash memory is actually divided into 4 kilobyte uniform sectors from the factory. So essentially, the chip internally has divided that whole 512K space into, let's say, 4 kilobyte chunks. And using some specific address lines, we could actually address or point to those sectors when we are doing, let's say, the write operation. And those sectors are actually could be addressed or could be called using the address line from 12 up to address line 18. So if we, let's say, look at the chip, remember that in the previous slides, we talked about that actually address lines 15 all the way up to 18 are actually controlled through our bank register. But now let's forget about that for a minute and just look at the chip in general, that we have address lines from A12 all the way up to A18 that we could use to select a specific sector on the chip. Now, according to the documentation, if you want to actually point to a specific sector, you're just going to set the value on those address lines. For example, the sector 0 on these chips are actually indicated when you have all these address lines set to 0. And that means that you're actually pointing to address 0 all the way up to 4095, basically the first 4 kilobyte on the chip, right? So this is the address range in flash memory that we are pointing when we are actually pointing to sector 1. Now, logically, if you just add 1 to these address lines, meaning that if we set A12 as 1, then essentially we're jumping to the next address space, and we can call it sector 1 essentially, which that means that our address range will be actually from 4096 all the way to 8191. And this is quite logical, right? Because if you think about it, by just changing this last 7 bits, or the most significant 7 bits, we could actually point to different, again, memory spaces inside our flash. And if you think about it, if you actually divide the 512 kilobyte flash into 4 kilobyte chunks, then we are going to get 128 basically sectors, starting from sector 0 all the way up to sector 127. So again, this is some sort of division, or let's say architecture, that has been done in factory in those chips. And basically, we need to know the address of these sectors because for the write operation, we actually have to send the sector number in one of the commands in order to erase the sector. And that's the whole point here. Now, combining that with what we actually had in our design, because remember, we had a 4-bit bank selector, which actually are borrowing the last 4 bits in our, or the 4 most significant bits in our address line as a bank selector, right? So you see that we actually, by creating those banks, we have made our life a little bit more complicated here. But again, let's just assume that we are using those for our bank. However, those 4 bits are still part of the memory address lines in our flash memory. So we are left with actually only 3 bits that we could combine with our, let's say, bank ID to come up with a total of 7 bits to select a specific sector. And if you think about it, in our design, each bank is actually consists of its own 8 sectors, because if you remember, each of our banks had actually 32K of memory. Therefore, if you divide 32K by 4K chunks, we're going to get 8 sectors per each flash bank. So flashbank 0 is going to have 8 sectors, flashbank 1 is going to have its own 8 sectors, and so on, right? Now, how we could actually point to a specific sector then when we actually have those addresses divided? Well, the point is that if you just, do a binary AND between the bank address and also the other remaining 3 bits, you're probably going to come up with a value that could point you directly in the sector that you want to, let's say, erase. So let's have a look at actually 2 examples that may help further clarify the point here. Let's say that we want to actually write a byte to address 8192 on our flash memory, right? In order to do that, according to our flash memory documentation, first we need to actually erase the sector that specific memory location is located in, right? So that means that we actually have to, let's say, erase sector 2. So in order to do that, we need to find the sector ID or sector number first and pass it into the chip, as you saw from documentation, through some cycles, so that we point to that specific sector that needs to be erased, and then the flash memory is going to erase it and make it ready for the write operation, right? So our target here is actually to find the sector ID or sector number. In order to do that, if we actually come and do a binary add between the bank ID that we have and also the relative sector ID, which is here sector number 2, which is the 3rd sector in that memory bank, then we could actually come up with the exact sector ID or the absolute sector ID across all the flash memory that we need to point to. So here, as you can see, when we're trying to write to, let's say, sector 2 on flashbank 1, which actually is wrong, this is flashbank 0, I'm sorry, this should be flashbank 0, we need to first set the sector address to the following. So if we actually do a binary add between these 2, then we're going to come up with number 2 decimal, which is again equal to 2 hex. And we are passing that sector address here, 2 hex, into that command in order to erase that sector. Once the sector is erased, then we could go ahead and basically do the write operation. Now, you may think that's quite inefficient because we're actually, erasing the whole sector from 8,192 all the way up to 12,287 just to write a 1 byte into that specific memory location. But I guess this is just the way that these flash memories work. So let's have another example. Let's say that we want to actually write a value to sector 5 of flashbang number 3. So in this case, they are highlighted with yellow borders here. And if we actually do a binary add between the flashbang ID and also along with the remaining 3 bits here, we could actually point exactly to the absolute number or absolute sector number across all the flash memory for this memory space. And as you can see here, I'm just doing a binary AND of the 7 bits, and essentially by multiplying the higher 4 bits by 8 and adding the number 5, which is the lower bytes, to it, we come up with the decimal 29, which is equal to 1D in hex. So again, when we are trying to erase the sector, we are passing 1D as the target sector along with a specific command, and that causes the flash chip to actually erase that sector. Once the sector is erased, we are ready to do the write operation. So I hope that it has been clear. I tried my best to describe the operation here, but if it is not fully clear here, I guess we could look at the sketch that I wrote, and probably there, when we are actually running some examples, it's going to be much clearer. The only thing that I really want to emphasize one more time here is that that division of the flash memory using banks is something that we came up as a logical way of dividing our flash memory. This is actually not part of the design of the chip or something like that. We just had to do that because we only had 32K of the memory address register address lines to address basically our flash. And that's why we had to divide it into 32K chunks so that we could use our memory address register. However, the sector concept is actually something by design. It's part of the chip architecture. And again, the chip doesn't see it as a 7 sectors per bank. The flash memory actually sees all the sectors from 0 all the way up to sector 127 as the sequential sectors starting from first address in the memory up to the last address in the memory, as you saw it in the previous slide. As you can see, these sectors are all sequential, starting from 0 all the way to maximum address available on the chip. However, here, because we have that division of the bank, of course, we left with 3 bits. We have to be kind of creative and kind of do an AND so that we come up with a absolute value for the sector number. So now let's go back to the chip documentation, and again, I think we went through those, but just want to make sure that we have a clear understanding of the operation of the chip. Again, we have some other commands that are available to us in this chip, and for example, if you want to actually erase the whole chip, then you need to follow again specific steps, which are 6 cycles here, and basically you need to send those commands back to the chip so that you could erase the whole chip. But normally when we actually want to, let's say, write something to a specific memory address in our flash memory, we just need to first erase the sector and then do the write operation through this. All right, so with that, I guess we are ready to go ahead and have a look at the sketch and see how it works and how we could actually read and write to our flash memory. All right, so let's go ahead and test our flash memory. So I'm gonna mount it to our Arduino shield, and And also I'm gonna add our LED board as usual. with that, let's just connect the power, and we should be good to go. All right, so let's have a quick look at the sketch and see what we have, and then we're gonna come back to the LEDs. All right, so we have loaded our sketch here, and by now you should be familiar with the first section of the sketch, which is really all about resetting the pins and everything. We have just a couple of functions again here to test our flash memory. The first step is really to just reset all the pins and set everything to default. And then the next step will be just to resetting our memory address register. And we talked about this function in the previous video, which basically what we're doing here is just setting a value of the 0 onto our bus, and then reading that value into LSB and MSB of our memory address register, so that our memory address register is actually resetted to a value of 0. Just some sort of initiation of our memory address register with 0. Now after that, we have two functions here. That one of them is reading the flash memory and basically printing the content of the flash memory into screen, and the other one is actually writing into a flash memory and populating our flash. So let's first look at the read operation. Now for read operation here, I'm actually passing 3 parameters. The first parameter here is the bank ID. And again, we have divided our flash memory into 16 banks, and I'm just passing one parameter here to select the bank ID that we will be reading from. The next value is the relative sector ID inside that bank. Again, going back to that slide, we said that each of those banks actually have logically 8 sectors, and this is basically a sector ID or sector number that is pointing to a specific sector inside that flash bank. And if you look at it, just I want to make sure that you get that point, that this sector ID is actually a relative sector ID. It means that it's a sector ID in the bank. So the range for this value should be from 0 to 7. Okay, so if you think about it, for each flash bank, we have 8 sectors, and we have a total of 128 sectors for the whole flash memory. But here we're pointing to the sector inside each flash bank. All right, so that's why we have a value of 0 to 7. And finally, the last parameter here is just a number of steps that we want to count and read the value of the flash and basically print it on the screen. So let's have a look at this function step by step and see what is happening. So stepmar and read flash is a function here. For this function, the first line is just basically just printing the fact that we are stepping the mar and reading the address lines and content of the flash. But the first operation that we are going to do is actually setting our flash bank, right? So we're calling upon a function called setFlashBank, and we're passing that parameter, that value that we set when we're calling the function. So let's first look at this setFlashBank and see how it works. So setFlashBank is quite simple, right? We talked about it in the circuit, and we said if you want to actually set a specific flashbank, the only thing that we need to do is that write that bank ID on the bus, and then read it into our flash selector circuit. And that's what exactly what we're doing here. You basically just write that value. Let's say we passed a value of 0. We are pointing to flashbank 0. We write that value to the bus, and then we're just bringing the EC and HI signals high. Remember, from the circuit, we had to basically set those highs, and then we need to pulse the clock. And once we did that, whatever is on the bus will be actually read into our flash bank selector register, and then it's going to show up on our output. So essentially, using this function here, we are just pointing to a specific flash bank. So this is first step in our function. And then the next step would be to actually, you know, find the first memory address that we are trying to read from. Now, remember that we are passing a relative sector ID to this function. And the relative sector ID basically needs to be multiplied by 4096. Why? Because each of our sectors are actually 4096 bytes long, right? So let's say that if we are actually pointing to flashbank 1, then the first address will be 4096 in our memory when we're looking at it, right? And this is, again, the first memory address that we're trying to read. Let's say if we actually pass a value of 0 as the relative sector ID, meaning that we are actually looking at sector 0, then obviously the first memory address will be 0. So we start from address 0 and so on. So I hope that this part is clear. Now, the next step is to actually set our MAR, right, with that memory address, because that's where we are actually trying to start from and then count for that number of, let's say, steps that we need to read the memory. So obviously, we are using set MAR, which is one of the functions that we talked about in the previous videos. And if you remember from the RAM module video, we talked about that set MAR, which basically just gets a value and set it as high byte and low byte into our memory address register, and basically set our MAR to that specific value. That's what it does. And once we had that, memory address register set to that first memory address, then we could start the counting operation on our memory address register, which is done with this line of code, which is digital write CME. And if we actually go back to the circuit, I guess that should be quite clear. We're actually bringing this line high so that this counter actually starts counting from whatever address we have set on our memory address register. Now, after that, we are just going through a loop because, again, we specify a number of steps that we want to actually count from that specific address. And then through that for loop, what we're doing is just, setting the RAM out signal low and then read the value on the bus and then basically print it on the screen. That's all we do here. However, here I have added, a couple of more lines so that we not only print the address and also the value, we also print the bank ID, which we have passed to the function, and that basically shows us on the screen that which bank we're actually pointing at each point of time. Unfortunately, on the LED board, we don't have any LEDs that are connected to our most 4 significant bits, which basically shows our bank ID. However, maybe, I don't know, in the future versions of the LED board, I would add those 4 LEDs. But for now, since we are printing those bank IDs on the screen, I guess it should be quite clear. All right, so this is really all about it. So stepping our memory address register and reading the values based on the flashbank ID and also the relative sector ID. So I guess when we run it, it's going to be probably more clear. So I guess also that's all about it. So let's go ahead and try it. All right, so let's just set the bank to 0, and also we're gonna set the sector to 0, and we're gonna read 16 bytes from our flash memory. All right, so let's just check this sketch and run it and see what will happen. All right, as you can see, we actually started from, bank 0, which is shown here. And then we are, again, starting from sector 0. That means that we are actually starting from address 0. And we are outputting the data on the screen. Now, as you can see, the data that is currently stored on all memory cells in this flash memory is actually FF, and it's 255 in decimal, and that's normal. Basically, these chips, when they come from the factory, they'll reset it to all FF on all memory cells. So that's good. Now let's do another thing. Let's actually change the sector this time. So we're still pointing to bank 0. However, we are pointing to sector 1 inside that bank. And let's see what will happen if we actually run this. Okay, so now that we have actually changed the sector, you see that the first address actually has changed to 4096, because this is the first address in sector number 1 of our flash bank. And the bank is still 0, as you can see. However, if you look at it, you see that that bit actually went high, and that is actually pointing to sector 0, excuse me, sector 1 at our flash. So if you go back to, let's say, our slides, essentially we are pointing to, bank 0. However, we are pointing to sector 1 of that bank, which means that our first address is actually 4096, which is actually consistent with what we see on the screen. Now, so this is really all about the read operation. Of course, we could, increase that number. Let's say you want to count 64 steps from, let's say, bank 0 and let's say sector 2 this time. And let's just run it to just show you how it works. All right, so now this time we are actually pointing to address 8192, which means that we are pointing to sector number 2 in our first bank. And again, we are counting for 64 steps, meaning that we are actually reading 64 memory cells or 64 bytes from our flash. Okay, so I hope that this part is clear. Now let's move on to writing to the flash. All right, so I have a different function here to write to the flash, and that's what we call it, the populate flash. And basically what this does, it takes 4 parameters, as you can see on the screen. The first parameter, again, is our bank ID, which has a range of from 0 to 15, because we have a total of 16 banks. The second parameter, again, is a relative sector ID, again, ranges from 0 to 7. The third parameter is actually the number of steps that we want, again, to, let's say, write to it, meaning that the number of bytes that we want to actually write to the flash. And then finally, this is the value that we are actually trying to write to our flash. So let's set that to 100. So now we're trying to actually write to bank 0, sector 0, and we're gonna write 8 bytes into it, and all of those 8 bytes will basically write a value of 100. Now let's look at the populate flash function to see how it works. The populate flash, the first line is just basically printing that we are actually writing to the flash. As you can see, again, the first step here is really to just set the flash bank, and we already passed that value through the function. So we're gonna set the flashback to that specific flashbank that we want to write to. However, now we have to calculate the first memory address that we are actually trying to write to. And again, that is calculated using our relative sector ID multiplied by 4096, as we discussed in the previous function. So that gives us the first address. And the last address will be just basically the first address plus number of steps that we need to go ahead, and basically that's going to give us the last address. However, we have another thing here, which is called the absolute sector ID. And the absolute sector ID means that what is actually the sector number across the whole flash memory, right? I guess we talked about that in the slides. And I said, in order to actually calculate the absolute sector ID, we need to, multiply the flashbank ID by 8, and then add that relative sector ID, which is the value that we are actually passing to the function. So if you go back to the slides, you remember that here, we actually did the same operation here. I said that you need to multiply, that 4 most significant bits by 8, and then add the lower 3 bits to it so that we actually come up with the absolute sector ID across all the flash memory for the specific address. Now, why we need that? Because we need actually to pass that into our flash in order to erase that sector ID. And that's what you see here. So as you can see, despite the fact it was relatively complicated in the documentation, it's not really that difficult to erase a flash and write to it. So as you can see, I'm just writing to the flash a specific value to a specific address. And this is the first step in erasing the flash. So if you go back to actually the documentation for our chip, you see that when we are actually trying to erase that sector, we need to point to address 5555, and then we need to write a value of AA to it. And this is the first cycle. And that's exactly what we are doing here in this line. Now, we are gonna basically do all the steps back to back in the sequence that is indicated in the documentation with that specific address and value that we need to send. However, in step 5, as you can see, or excuse me, step 6, you see that finally I'm actually sending the sector ID, which is our absolute sector ID, plus a command of 30, which tells the flash memory to actually erase that specific sector. And then we're creating a 2-second delay here, I guess, just to give the chip enough time to clear the flash memory. And to be honest, I just came up with 2000 milliseconds or 2 seconds here. I'm not sure how much time it is required. We could probably look at the timing diagram, but I just wanted to take it easy and just give it 2 seconds so that the clear operation is completed. And then once it is done, then we go into a write operation. Now for write operation, we're going to start from the first memory address that we calculated here. And then we're going to go all the way up to last memory address, which is basically, number of steps plus the first memory address. And then we're going to write the value that we passed into the function. Now, if you look at it, you will notice that for every byte that we trying to write to those memory cells, we actually have to, again, repeat a specific procedure here. And again, those specific procedures are actually coming from the documentation for byte program section, that you see that if you want to write something, then we have to at least have these 3 first steps executed before we actually send the data to the chip. And that's what is happening here. We sending a couple of commands, and then finally we are sending actually the address that we're trying to write, and also the value that we want to basically write to the chip. And then again, another delay here just to make sure that data is actually written to the flash memory. And finally, we set all the bus pins and address pins to basically input. And of course, since the next step will be to read from the flash, I'm just setting the memory address register address to the first memory address here, and then we're gonna basically count or step it and read the values and print them on the screen. Now, the only thing that we haven't looked here is write to flash. And let's see what write to flash does. Write to flash is quite simple. When you send, basically when you call write to flash function, you're passing 2 parameters. The first parameter is the address that you're trying to write, and the second parameter is the value. So as you can see in the write to flash function, again, we are using a set mar function to set the address, right? And then we're going to write that value that we want to write to the memory into the bus. After that, we create a small delay, and basically we're just, bringing the RAM in signal high and pause the clock. And that's what we had in the circuit, if you remember. In order to write to this memory, we need to bring the RAM in signal high and pause the clock. And remember, by this time that we are actually doing these signals, we actually have set the address and the value. So that's all about it, really, in order to write to our flash. The only thing that is important here is that we actually have to send a specific command to erase it. And once it's erased, again, we need to send a specific command in order for the flash memory to be ready for the write operation. So with that, let's just go ahead and run a couple examples and see how it works. So the first thing that we're going to do, we're going to actually move this function to the top, and we're going to write something to, let's say, bank 0 and address, let's say sector 0. And this is actually step we wanted to first populate it, sorry. All right, so let's just remove that. All right, so we're gonna actually write to bank 0, sector 0. We're gonna write 8 bytes to it, and we're gonna just write value of 100 to it. Then we're gonna read the same, location. So bank 0, sector 0, and we're gonna actually read it for 16 bytes. All right, so let's run that. Looks like I have an error here, which, all right, so let me clear the screen and let me just run this. So as you can see, now we are writing to the flash, and writing to flash completed. And now you see that in bank 0, sector 0, we are actually written a value of 64 for 8 bytes. And as you can see, the rest of memory locations are still having a value of 255, which is just the default value. So it clearly shows that we were able to successfully write to the first 8 bytes of bank 0, sector 0. So, all right, with that, let's actually try writing to another sector, just to show how this thing works. So now this time I'm gonna actually switch to, let's say, bank 1, sector 5, and I'm gonna write a different value to it. Let's write I don't know, 172, and then I'm gonna read the same bank and sector, and basically the same thing. All right, so with that, let's run it again and see. Let me clear the screen first. I'll run it again. So we're kind of repeating, the same thing that we did previously, but now we're writing to a different bank and different sector. And as you can see now, we are in bank 1 and sector 5. And again, if you look at our slides, you will see that actually sector 5 start with address 20,048. Or 5,000 in hex, and the data that we're actually writing to it is 172, as we indicated in the function. So with that, it is I guess quite clear how we could read and write into our flash memory. All right, I hope that this video has been informative. In next video, we will be building a flash programmer, which is a simple circuit that could help us later in programming our flash memories outside basically our computer. Let's say that we develop some microcode later, and we wanted to basically write those microcode into our flash memories. Then we could just use that simple flash programmer to do so. However, in this read and write operation from inside the computer, as you can see, is a little bit more involved, meaning that we are actually have to follow a specific procedure in order to write or read from, or mostly write into our flash memory. And that's why probably later, if we really want to, let's say, save a file or a value into our flash memory, then we need to come up with a little bit of a code. Basically, we need to develop probably a mini file system, let's say, to take care of these preparation steps before we actually write the data into our flash. And that's actually has been done quite well by Carsten in his minimal project. All right, with that, I hope that this video helped you guys to understand our flash memory a little bit better. And I'm gonna see you in the next video.